Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. I welcome you all into my today lecture. Today is our lecture number 15, Unit 12, Current Electricity. Our today's topics are thermocouple, variation in thermoelectric EMF with temperature, Kirchhoff laws, which comprises on two parts, KCL and the key part. And inshallah, we will explain these in great detail. It is one of the most important and significant part of our today lecture. So let us start with the name of Allah Almighty. The first topic is the thermocouple. Now, what is the thermocouple? Thermocouple is a thermocouple is used to which it is used to convert electrical energy into what used to convert the heat energy, sorry, it is used to convert heat energy into electrical energy. Heat energy into what? Into electrical energy. Now, one important point which I want to share with you right in the beginning is I should not forget it later on then. It is the point where I want to tell you that remember the EMF or that electrical energy produced by the thermocouple is of the order of what? It is of the order of milliamperes, right? In within the milliampere. So what this mean that the EMF produced here is small, then why we are after the thermocouple, right? Although EMF, the EMF reduced by the thermocouple, by the thermocouple effect is very small, but the effect caused by it, the effect caused by it is very large. What is that large effect? For example, it can be used as a sensor in most of the electronic device, for example, temperature or heat sensor device, right? Which can even detect minute change of temperature, right? Now, what is thermocouple? Thermocouple is formed when two dissimilar atoms, when two dissimilar metals are joined at one end, right? An electric potential called the Seebeck voltage is generated, which is proportional to the changes in the temperature at the joint. So the thermocouple consists of two dissimilar atoms. I'm very sorry, two dissimilar metals. That is one right here you see, for example, the aluminium, and the other is the iron, right? There one end which is joined at a temperature of what? At the temperature of 0 degrees centigrade, for example. See here like this. And the other end is connected to the potential difference source, and the other end, the other giant, they are at what? They are at relatively higher temperature. It is kept at which temperature? At the room temperature here, as you see. Now there is another clear diagram. As you see here, we have two wires, the wire of type A and the wire of the type B. They are to consist of two dissimilar metals, right? This is, for example, metal A, you may say aluminium. This is metal B, you may say the iron or the copper or whatsoever you like. This is the hard junction. You see here, here we have what? The hard junction. As you see, it is being heated, the temperature is increased here. So let we call here the temperature is T2, and there will be a temperature that is the other two junctions are at a temperature. We say that they are at the temperature T2. that is called the sorry, T1, this is T2, that is called the cold junction. So the change in temperature delta T will be equal to T2 T2 minus T1, and let's say it has some value T. This effect, the thermocouple effect, was first discovered by Thomas Seebeck in 1821. 1821, right? And he did it so by joining two wires of two dissimilar metals to form the circuit. As you see here, the circuit consists of what? The highly sensitive voltmeter or galvanometer, which can detect the EMF source within the circuit, and it is in the range of the that is the milliampere, and for more precision, the millivolt, and for more precision, the microvolt will be best, right? Why? Because the EMF produced is very small. And now the uh, one junction is kept at a higher temperature while the other junction remain at relatively very much cooler temperature, and that is what we can say that at 0 degrees centigrade in the ice. And there is the galvanometer, which I already told you can detect any current or the EMF changes within the circuit. The current result by this, yeah, the current caused by this is known as the thermoelectric current, right? That is called what? The thermoelectric current, right? And I guess the direction of the thermoelectric current is, let's say, by this way, from the hotter junction to the cooler junction. Now, experiment shows that the thermocouple effect experiment shows that the induced EMF, the thermoelectric EMF, this one, reduced during this process is directly proportional to the temperature changes, right, at the hotter junction. And here you see the coefficient, this alpha, this is called the thermoelectric coefficient. The thermoelectric, this is called the thermoelectric coefficient, the thermoelectric coefficient of the metal, let's say A, and then definitely this will be for the metal B, and it purely depends on what? Depends on the nature of the metal used during the experiment. So the most important features here is that it depends on what? That it depends on the change in temperature. Greater the change in temperature, greater will be the induced EMF. And during this process at the junction, the heat energy, this heat energy is actually converted into what? Into electrical energy. As long as there are two dissimilar metals, they are joined at the junction, then there will be induced EMF. So when you use similar metal, you wouldn't be able to see this effect, right? The magnitude of the thermoelectric EMF depends upon the nature of the two metals and on the temperature difference between the terminal. Here in this diagram, you see a little bit another perspective. That is, you see the hard junction here. As you see, this is the hard junction, and here you see the cool junction, which is kept at ice. And then you see, look, this is what? This is the as you see here, this is the iron, and the copper, dissimilar metals, they are joined together, and the current flows here is from the current that flows from the from the cooler junction, the actual current direction, it is towards the hotter junction. Now you see there is galvanometer connected in the circuit, and the galvanometer will indicate any uh, EMF changes within the circuit, right? So the Seebeck investigated the thermoelectric properties of the large number of metals and arranged them in series known as the thermoelectric series. Please note this point, and I'm pretty sure that when you see this thing in your textbook, you will seriously get disturbed, right? Why? Because there is no proper explanation to the series known as the thermoelectric series, and you will only find a kind of sentence like this. If you refer to your book, it might be somewhere there. So the Seebeck series given below is that it consists of these elements just like a triboelectric series. Now, when you see that when any two of these metals in the series is used to form a thermocouple, for example, this one, look, you may use this one, you may use these two, you may use these two, or any of the two combination you can use. And the most interesting thing here is that the thermo EMF is greater when the two metal use are the farthest apart in the circuit, right? So that the farthest they are apart, then the greater will be what? The induced EMF produced in the circuit. No EMF changes when the junction temperature is the same. So of course, there will be no heat flow, and then there will be what? There will be no EMF in the circuit. Now, the next important point here is the variation of the thermo EMF with the temperature. And this can be demonstrated by drawing a graph between the thermo EMF and the temperature. To study the effect of the difference of the temperature of the two junction, consider the two thermocouple of two dissimilar metals A and B as shown above. Let me bring this here. Let me slide this to this position so that it is in front of you. Oh my God. Like this here. Let us see, look at this diagram here, that the two dissimilar metals A and B, which is here. Now consider the core junction is at the temperature 0 degrees centigrade, as I told you, kept in ice, and the temperature of the hotter junction is raised gradually. This is the hotter junction temperature, as you see like here. Now, the experiment shows that the thermo EMF varies with the temperature of the hot junction, and the graph of the variation of the thermo EMF in the circuit with the variation of the temperature at the hot junction is shown here. Now, as you see, look, this is temperature and this is the EMF taken along the y-axis. You see that as the right when both are at the same temperature, like here at this position, then what is going to happen? There is no EMF. The EMF is 0. Now, as the temperature T, the temperature difference, as it increases, then you see that there is gradual increase in the thermo EMF. As you see, the thermo EMF increases as the temperature increases. So that is the temperature of the hot junction at which the thermo EMF in the thermocouple becomes maximum is called the neutral temperature. So this is the neutral temperature. At the neutral temperature, the thermoelectric current is maximum, means that the thermo EMF is maximum, right? For a given thermocouple of two metals, the neutral temperature has a fixed value. This value remain constant for the given pair of the metals. On further increasing the temperature of the hot junction after the neutral temperature has reached, the thermo EMF decreases rather than increases. As you see, look, there is then gradual decrease in the thermocouple EMF. The thermo EMF decreases and becomes equal at a particular temperature called the temperature of and become equal to zero, right, at a particular temperature called the temperature inversion, is you see here like this one. At this temperature, the thermo EMF fall to zero. Beyond Ti, if the temperature of the hot junction is still increased, now when you increase the temperature of the hot junction any further, then what happens? There is an interesting thing, and that interesting thing is this one. You see that, look, the graph still continues to move, right? So what does this means? That you know that potential difference, positive or negative, like this. What does this mean? That again rise in EMF. But what happens? The direction of the current now reverses. So if you increase the temperature beyond that level, then what will happen? The direction of the current get reversed, right? Now, the the rate of change of the thermo EMF with the that is with temperature, this one is called the thermal power or the Seebeck coefficient. That is the ratio of the induced EMF to that of the change in temperature. This one, which can be calculated from the slope of the graph, is called the thermal power or the Seebeck coefficient, right? So the much of the explanation is missing from your book, like why this stop here and why then it reverses the direction when you increase the temperature in one direction, means that if you keep on increasing and not decreasing. Okay, so that is missing, and I think it is beyond the scope of the syllabus and to discuss this thing here. Now let us move on to the next topic, and the next topic is the Kirchhoff law. Now, what are the Kirchhoff laws? The KCL law or the junction rule. That, what is it? You know that when you were in class 10, your teacher told you about the combination of resistors, right? Combination of resistors are various components. There were the series combination. Even we discussed this here also, and there is the parallel combination of resistor, the series combination of resistor, and the series and parallel, and then there is the complex combination of the capacitor. So for the simple series and parallel circuit, it is easier to just simply apply the Ohm law and to calculate the equivalent resistances and other physical quantities for the circuit, right? And that is when it is series or when it is parallel. And if it is series and parallel, then you know the parallel part must be solved first and the series part must be solved second then. But there are certain circuits where it is very difficult to solve. For example, you cannot use the simple basic rules for series and parallel combination when you try to solve circuit like this where there are two EMF sources, right? Like that or like this one. So that is very difficult to solve. Or when there are more branch currents, right? So for that reason, we use the Kirchhoff law to solve such problems or to address such problems. There are two Kirchhoff laws, and the Kirchhoff laws tells us the KCL law or the junction rule. This law states that the algebraic sum of all the branch current at the junction is zero. What? The algebraic, the algebraic sum of all the branch currents, all the branch currents at the junction, at the junction, at the junction for any electric circuit is zero. At the junction is zero. What does this means? That sum of all the branch current is what? The branch current at the junction is zero. And for this summation, maybe let me write it like this. For example, if you have I start from 1, if you have n branches, then I will be equal to 0, right? This is based on the law of conservation of charge. Based on what? Based on the law of conservation, of charges. That charges are neither created nor destroyed. So junction, now what do we mean by the term junction here? Junction is what? Junction is the point where two or more wires, conducting wires meet, right, within the circuit. So that is junction. This is a junction. This is a junction. So at the junction, because you know charges are neither created nor destroyed, so the total amount of the charges within the circuit remain constant. So the current that ends is always equal to the current that outs. And what does this mean? That the current, sum of all the current entering at the junction is equal to sum of all the current that leave the junction. And if we take the current at the junction, leaving the junction is positive, then the current entering the junction is taken positive, then the current leaving the junction will be taken negative. In n, it will be taken positive, right? And that which leaves will be taken what? Will be taken, and they will be taken negative, right? It will be taken negative. Remember, but this is just, it is already a solved equation. For example, it will be like this. You just see here, look, this is entering the junction. This is what? Entering the junction. This is entering the junction. These two, they are leaving the junction. So what will be the required equation? The current that enters the junction always taken positive. I1, and that is I5, and then this is I4, I think. They enters the junction, and which leaves? The I2 and the I3. So you see, let me do it like this. For example, I2 minus I3. So you see they are negative because they leave. They are positive because they enter the junction, right? So here the equation will be looking like this, that the n, so I start from 1 up to 4. Yeah, I start from 1 up to 5. These are 5, right? In, it will be 0. But just keep this one thing in your mind, that the current that enters will be taken positive, and the current that leaves will be taken, they will be taken negative, right? So that is the first part of the Kirchhoff law. And when we solve the circuit, we will use these things later on. The second part of the circuit, which is also most important, is the KVL or the loop rule. Now, what the KVL or the loop rule say, it says that is the algebraic sum of what? In any closed circuit, what? In any closed circuit, the it is important that the circuit must be closed. That in any closed circuit, the the algebraic sum of the algebraic sum of all the algebraic sum of all the algebraic sum of all the EMF sources, all the EMF sources, and the IR drop, and the IR drops. The IR drops, I means voltage drop across the resistor. The IR drops is equal to what? Is equal to 0. Yeah, what does this mean? That the algebraic sum of all the EMF sources and the potential drop across any resistor is 0. Yeah, the algebraic sum of all the EMF sources and all the terminal potential differences in the circuit is equal to what? It is equal to 0. It is based on the law of conservation of what? Based on the law of conservation of energy. Conservation of what? The law of conservation of energy. It is based on what? It is based on the law of conservation of what? The law of conservation of energy, that energy is neither created nor destroyed. For example, if you look into this circuit here, let us see. Look at this circuit here. Now, in this circuit, you see that there are what? That there are the EMF sources. The EMF sources, this one, the E2, the E1 sources. So definitely these are the EMF sources. So you have input 1 and you have input 2. And now where are the energy dissipated? In the load resistance R2, the load resistance what? R1 and R2. So across this there will be IR drops. For example, IR1 and IR2, and this is IR1. Right? So that will be the potential drop across this sources. So you know that these are our these are in fact output. So definitely whatever the amount of energy we supply, we can get for an ideal system the same amount energy back. So this is why they says that the algebraic sum of what? All the EMF sources. The algebraic sum of what? The algebraic sum of all the EMF sources. And if I write it in my own way like this, if I just mark this, I start from 1 of 2 n, then I will be write it like EMF source I plus all the potential terminal potential drop 1 to n, like this will be 0. Okay, but this is there might be a question, and it will be telling to you to verify the that show that the Kirchhoff's second rule is based on the law of conservation of what? The law of conservation of energy. Now there are certain rules to apply for solving this circuit calculation. Okay, that is first let me show you how it is based on the law of conservation of energy. Okay, even if this part remain this solving any question by using the Kirchhoff rule or law, then I will do that later on. Okay, but this is, let me show you how it is based on this thing. Now look, in order to solve or to apply such situation, then there are certain rules, okay, that we call the convention for applying KCL law. Convention for applying the KCL law. Now, what is the first rule? There are two things which we can do. First of all, the first thing is the assume current direction. Assume current direction. First of all, to solve this, you must have what? That you must have the assume current direction. The assume current direction can be clockwise or it can be anti-clockwise, purely based on your choice. But remember, once you consider the current in a direction of your own choice, then stick to it. Don't change it down the road. It will be the first thing. Don't worry if you take clockwise or if you take anti-clockwise. It doesn't make any difference. For example, that even if your assumed current direction is wrong, then later on at uh, the end of the day, or when you finish your calculation, then it will be corrected in a way that if your assumed current direction is wrong, then there will be one extra negative with your current, right? That will tell you that whatever current you assumed, that is wrong. So don't worry about it. Okay, you can choose any. But I will tell you a very simple technique. And what is that very simple technique? The simple technique is that always choose from that is from the greatest source of EMF. From what? From the greatest source of the any EMF that is present in the circuit. This is what I am saying. It is not necessary. You can choose from the smallest one also. So look, for example, if I suppose that E1, the source EMF 1 is greater than the source EMF 2, and I say that I choose the current direction like that. So this is why I have chosen from this direction, and I say the net current is this one. A, that is, and this for the mesh or for the circuit A, B, C, D, A, this is a closed circuit and a closed path. The second important point here, this is point 1. The second point here is that is a rise in potential. What? A rise in potential. A rise in potential is taken positive. Is the rise in potential is taken positive. And a drop in potential, a drop in potential, a drop in potential is taken what? It is taken negative. It is taken what? Negative. Now remember here one important thing, that the positive terminal of the battery, positive terminal, it is taken at high, it is considered as high, and a negative terminal of the battery, it is taken as at low. So if you move from positive to negative, then this is what? That is, this is drop in the potential, okay, because you are moving from high to low, and it will be taken as negative. But if you move from negative terminal towards the positive terminal, then this is, you are moving from low to high, so it will be taken as positive. So a rise of potential is taken positive. Why? Because, for example, if you have a positive charge, and if because always choose this is one important thing. Thanks God, I just got this to remember. Like, that is conventional current direction. Remember, we will use conventional current direction. So when a positive charge, when it moves from negative terminal of the battery in the circuit towards the positive terminal of the battery, work must be done, right? And that work done on the charge is taken as positive. Why? Because that it will gain energy, right? And when it moves from the positive charge, moves in the direction of the field, right? That is from the positive towards the negative, and then it will lose energy, and the loss of the energy is taken as negative, right? So this is what you will remember. The fourth important point here is, for example, look and see here. If I want to demonstrate to you, for example, look, if I just move in the direction of the current chosen from the point A to B, so you see here what is going to happen here. The from now, look, this is negative and this is what? Positive. So I'm moving from negative to positive. So this is what? From low to high. So if I so the that is what the rise in potential. Why? Because I'm moving from low to high. So I'm sorry. So it is rise in potential, and it will be considered as negative. And the next important point, this is for these two are for the EMF sources, right? What if the sources are what? If they are the IR drops, then what will happen for the IR drops? This part, the fourth point, and the point four. For the IR drop, that is when you are traversing resistors, right? And then the same situation happens, right? Just label, go always and choose that is. First of all, I just want to tell you that when you are calculating the IR drop, then you must remember one important point, that always move in the direction of what? In the direction of the assumed current direction. Assume current direction. That will facilitate you the best. So look here. For example, look at this yellow arrow as I'm moving from what? In the direction of the current. So definitely if I'm moving in the direction of the current, if the direction moves in this way, then definitely it will be the positive terminal and it will be the negative terminal. So you are now moving from point of higher potential towards the point of lower potential. So that is what? And that is the drop in what? That is considered as drop in the potential, right? And it will be taken as negative, right? So you have that as what? Negative. So the in the direction of the current, IR drop what? Very simple. The same principle is used, but here I am just doing a shortcut. That is the IR drop in the direction of the current. What? In the direction of the current is taken negative. And fifth, the IR drop in the direction opposite to, in the direction opposite to the current, the assumed current direction is taken what? Is taken positive. So this is what? Traversing resistors. What? I will simply call it traversing the resistors, right? That how we can traverse the resistor. So let me bring it to the another appropriate position. Look here. So now I just want to demonstrate to you how it is based on the law of conservation of what? Energy, the Kirchhoff's second law. As I told you, that let we apply all the rules right now here. Let I choose this point A and I just consider this, that the EMF source E1 is greater than E2. This is what I don't know. I just suppose this. And let my assumed current direction is from the greater towards what? Like this one. This is the assumed current direction. So what is my assumed current direction? My assumed current direction is what? My assumed current direction is in the anti-clockwise direction. This is the source A2. So let mark it like this. This will be then positive. See here, it will be taken positive. It will be then negative in the direction of the current. Similarly, this will be then positive and it will be negative as the current moves, as the charges moves in this direction from the point of higher potential towards the point of lower potential. Now, let us do this thing here. Now, as the current moves, right, the charges moves here in this way. Now, look, first of all, we have the source E1 here, right? Then as from the point A, when I move from the point of lower potential to the point of higher potential. So the IR drop, the EMF source, it will be taken as negative, right? And I'll be writing it as E1. So you know that, look, What is what is the work done? What is the potential difference or the EMF? Work done per unit charge. So what will be work done? It will be exactly equal Q, as you see. So in order to, it will be equal to Q into what V. Now, what is current? You know what is Q? It is nothing but it is I into T, the time for which the current flow into V. So in my this equation, what I will do, I will just write like this. So as you see, look, keeping this thing into my mind, the energy equation, that minus the source EM1, and let's say the current that flows in the circuit is I, and it flows for the time T, as you see. So this is the energy for the source EM1. Now second, again I'm moving from the point of higher potential towards the lower potential, then again the IR drop will be taken as a negative, right? And what I'll be writing here for this is like this one. You see that what is going to happen, it will be taken as negative, and here it will be now look, the it will how it will be like this one. The current first here, it is I R 1, this is the potential difference V, and for the rest I will be writing I into T, the charge for Q. It is for this equation. Okay, so let me just do this. As you see, for because I'm writing the energy equation here, this is the higher potential and this is a lower potential. So the drop in the potential is taken as what, that is the rise in potential is taken, rise in potential is taken positive. The rise, oh, this is rise, I'm sorry, the rise in potential is taken positive. Here there is drop in the potential because I'm moving from point of higher potential to lower potential. So there is what, drop in potential. The charge, the positive charge, will lose energy because it has to move in a direction of the field, right? So it will be taken as negative, right? This will be this one, and it will be E2 and the same I into T, right? As you see, we have one this thing. Clear? Now, the another important point here is, again, I'm just moving in a direction of the EMF. So what I will write here, minus, and it will be like the source I, and it will be R2 into I into T, into T. Now as you see, it will become equal to what, 0. And now look, this I into T, it is common everywhere. Let it get out of my equation, and what will be remaining here, E1, and I'll be having here minus E2, and there will be minus IR1, and then there will be what, minus IR2. As you see, look at this equation. Now this is very simple here. Look to this equation here. Now if you just see, what is this, nothing but this is my input. As you see, this part is the input. Why? Because this is the EMF source. And now you know that the two EMF sources oppose each other, right? They are in the opposing situation. And here, what do you see? This is my what? This is my output. And you know, input and output are the same for no energy loss in the circuit. So here, this is all the EMF sources like this one. I start from 1 up to N, so that is 2, and then here it is I. Like, let me do it like this way. You see, E1 minus E2 will be equal to what, IR1 into IR2. So the net EMF source here is equal to what, the net potential drop, the net terminal potential difference, right? So what does this equation shows? That this is purely based on the law of conservation of what, on the law of conservation of the energy. right? That sum of all the EMF sources within the circuit is equal to 0. So the negative sign only indicate that it is opposing the EMF sources, because the two batteries are connected back to back, you may say, like this. E2, and this is what they are flowing in a direction like plus minus IR1 into plus minus IR2, right? It is equal to 0. So you see, look, and this is the required equation, which tells that it is based on what? The law of conservation of energy, that energy is neither created nor destroyed. Why? Because simply this is what? This is the EMF sources and this is the potential drop. So the sum of all the EMF sources is equal to the sum of all the potential drop. So inshallah, this numerical is remaining and I tend to solve this to you, but let me do it in my next lecture, inshallah. But this is what I was thinking, that it is the most important point, that if you might have a question that show that the Kirchhoff second law is based on the law of conservation of energy, then you can prove it in this way. So thank you very much for today's lecture and see you in the next lecture.